Okay, so today is week 6. Excuse me. Uh, so today, like I said, is week 6, right? And this week, you would have covered in the course autoencoders, like that, right? So we will see some problems related to autoencoders, assignment like problems, right? And after going through the list of problems, we're gonna I'm going to do a little bit of hands-on autoencoder, very simple autoencoder that encodes MNIST digits, right? And we're gonna play around with it a little bit to try and understand uh, over complete, under complete, concepts of those kind of concepts, right? How autoencoders can enable basically compressed compression, right? Image compression specifically in this case. So yeah, so like I was saying, today is we're going to look into autoencoders, and we're also going to see Jacobian matrices. And after seeing some autoencoder problems, we're going to do a little bit hands-on autoencoder stuff, right? I build a very small autoencoder that can represent MNIST digits. And if there is time, I might show uh, I might show a notebook. So because we'll also be seeing Jacobian matrices, right? So it's probably a good time to introduce how the backward computation uh, is actually performed, right? So when you use deep learning frameworks, backward computation is typically hidden from you uh, under the automatic gradient uh, system, but it's instructive to know exactly how that happens. And it's for simple networks, like simple feed forward, fully connected networks. It's a pretty easy thing to implement. So we're gonna see uh, some example, at least one example, maybe if there is time, right? So let's start off with the material for this session. So we are talking about autoencoders. So autoencoders are a type of neural network architecture. Uh, it consists of basically two parts. There is an encoder and there is a decoder, right? And so the autoencoder, the concept of autoencoders is very old, right? And it's actually pretty much as old as the current paradigm of deep neural networks itself. It is as old as the idea of training deep neural networks with gradient descent backpropagation, right? So, and in fact, it is still relevant. This concept of autoencoder, this concept, even if it is not relevant by itself, but this structure of encoder and decoder, the structure is still extremely relevant, even in much of the uh, currently state-of-the-art models, all kinds of all kinds of application can be divided into encoder and decoder blocks, right? So in fact, the very famous transformer architectures that people use, ChatGPT and all. So they are what is called as a decoder only architecture, right? So it also, it's like a part of this encoder decoder structure. Of course, uh, things have grown a lot more complex than this initial uh, idea of a autoencoder, of an encoder decoder, right? Initially, the idea was to encode and decode static data, right? So static data like an image or well, well, an image, right? An image is a perfect example of a static data that you can encode into, let's say, a smaller size, and then you decode it back into its larger full size again, right? And then there were multiple evolutions of this idea. Went from fully connected networks to convolutional and deconvolutional networks, so-called units. Then we went to transformer architectures, and that's where the idea of uh, what you encode and decode changed. Instead of encoding and decoding static data like images with transformers, basically encode and decode dynamic time series data, right? So you take a whole chunk of text, right? And then you kind of encode it into some higher dimensional uh, representation, and then decode. And based on that decoding, you try to predict what is the future chunk of text that will be most appropriate for this given text, right? So you kind of the idea of what you encode and decode has changed over time. That's what I'm trying to say, right? So, like I said, autoencoders type of neural networks. Of course, we don't have to bother ourselves at this point with such highly complex systems. Right? We are dealing with very simple idea of autoencoders. Specifically, we are dealing with, let's say, a single hidden layer fully connected network, right? So you have an input X that goes into this single hidden layer uh, H, A1 and H1, A1 being the pre-activation, H1 in post-activation, and then this this thing then later goes into the output. And the idea of an autoencoder is that the input should match the output, right? So the idea is that you recreate the input at the output layer, right? And it is characterized like this. Smallest possible autoencoder is characterized by two sets of parameters. One is the W, which is the encoder parameters, and the other is the W star, which is the decoder parameters, right? And they have kind of the same shape, like or rather the same number of parameters. The shapes are transposes of each other, obviously, right? So yeah, so this is very simply put what an autoencoder is, and then you can in the abstract sense, you can then kind of instead of thinking of it as a single layer, you can think that there is an encoder block which has many layers. There is a decoder block which can potentially have many layers, and you can do all sorts of things with it, right? So we'll move on to the first question in this autoencoder stuff, which is that okay. So the input belongs to Rn, so this is n-dimensional input, and then you compute h1 as g of wx plus v, and h1 belongs to Rd, which is d-dimensional hidden layer, and output is x prime. The question here is what is the dimension of w star, which is the decoder rate, right? So you have options over here, d by 1, n by 1, n by dt by n, right? So and it takes some time and try to figure out what is the correct option. And then a couple of minutes, I will discuss the solution. You can share your answer in the chat. Mm, okay, so someone has answered. So that's good. Uh, yeah, so let's try to work through the problem, right? So we have input x is n-dimensional, then you're doing w times x, right? So it's n by 1 is x, which means w is d by n, right? Because your h1 has to be d-dimensional, and h1 is d-dimensional, and then you multiply w star, you get x prime, which, remember, it's an autoencoder, so x prime should have the same dimensions as x, which means x prime should be n-dimensional, right? So w times h1, or rather w star times h1, should be n-dimensional, which means that w star should in fact be n by d, right? So yeah, the answer is correct. N by d is in fact the correct option, right? So you get uh, h is d-dimensional, then you get w star times h1. H1 is d-dimensional, x prime is the same as x, so it has to be n by d, right? Very good. So given, yeah, so we have a question here. Given the following autoencoder, what are the possible dimensions of h1 and p star, right? So p star is this bias over here. H1, of course, is the hidden layer activations. This is very simple problem. If you followed the discussion of the previous problem, it should be very straightforward, right? So we'll just give like a minute for it to kind of work out the answer. Mm, okay, no one has answered, but still, let's carry on. Right? Uh, yeah, so like I said, based on the previous discussion, it should be fairly straightforward, right? Previously, we found out, obviously, know from here the given data that H1 is d-dimensional. The only thing is, whether it is a row vector, column vector. In fact, everything is here. All of the activations, in fact, seem to be column vectors, right? That's why they come after the weight matrix. So everything is a column vector, which means H1 must be d by 1, right? And what is B star? B star is the bias that goes into the output layer. Obviously, the number of bias variables that go into the output layer must equal the number of neurons in the output layer. So the number of variables B star should be n, because there are n uh, n dimensions in the input and n dimensions in the output, obviously, right? So B star also, B star should be basically n dimensional. B star should be, in fact, n by 1, right? Because we are dealing with uh, column vectors over here. So yeah, d by 1 and n by 1. Very straightforward, simple problem. Right. So moving on to the next question. So here we bring the concept of under and over complete autoencoders, right? So have certain statements which are in relation to what I'm calling an undercomplete autoencoder, right? A always performs loss-free encoding. B always captures only few features of the input. C dimensions of the hidden layer is less than that of the input layer. D dimensions of the input layer is less than that of the hidden layer, right? So there are four, and the question is which of these are true, right? So first of all, obviously, you have to understand what is an undercomplete autoencoder. So if you know that, then you can start reasoning out about these options, right? So once again, I will give a couple of minutes and then we'll see this. We'll discuss this. Okay. Let's see. Someone has answered C and someone B. Okay. So for this question, the language that is used in the options is actually kind of important, right? What you see here is that these language that is used is kind of absolutist language, right? So it like always performs loss-free encoding, always captures only few features of the input. Dimensions is less than that of the blah blah dimensions is of the hidden input is less than that of the hidden dimensions of the hidden is less than that of the input, right? So these are kind of absolute one, zero or one kind of statements, right? Which means that they're either true or false, right? And in fact, with uh, with this deep learning or with any kind of gradient descent based algorithm, right, which is at the end of the day a heuristic, uh, the output is kind of I mean what you get out of the model is probabilistic in nature, right? So this A and B are kind of, so because of because of the nature of these models, right, you can never really say that this A and B are going to be true, right? Because it's not always going to be loss-free encoding. It might do it, but most likely it will lead to loss-free encoding, especially because it is an intercomplete autoencoder, which come with the definition, obviously, and always captures only a few features of the input. Few, what is few? Uh, you know, what we can say definitively is true is the dimensions of the hidden layer is less than that of the input layer, because this is the definition of an undercompleted autoencoder, right? So when you say undercompleted autoencoder, it means that the uh, the encoding layer, right? That is the hidden layer where you are kind of encoding the input. So the dimension of that should be smaller than the dimension of the input, because that's how it is defined, right? So C is obviously true, and that which means that D obviously is not true, right? So like I said, these A and B kind of absolute statements will, things like this will generally not be true when you're talking about deep learning approaches, especially when you're talking about the outcomes of deep learning approaches, right? So yeah, like I said, capturing only few features is not guaranteed, though it generally happens. Any autoencoder cannot guarantee loss-free encoding. Even over-complete autoencoder not necessarily guarantees loss-free encoding, right? It can do it, but because the training process is after all heuristic, uh, it may not do it anyway, right? Even though it is over. The only thing that you can say with certainty is that you know dimensions of the hidden layer is less than the dimensions of the input layer. The, the corollary of this, is, of course, is that you can think of this kind of an undercomplete autoencoder as a compression algorithm, right? So you can think of it as that you are kind of compressing the input data into a smaller number of values, right? So for example, if you have MNIST data, which is 28 by 28 images, that is 784 values, and then you compress it to, let's say, 50 values, right? So that is your under complete autoencoder. So you train an autoencoder such that the hidden layer has just 50 uh, neurons, and then the decoder obviously has like whatever 784 neurons. So you can think of this like this action basically is a compression, right? So what previously uh, we were using 784 pixel values to denote. Now you are going to denote that with just 50 values, right? So it is more than 10x compression, in fact, right? So in that sense, that's what is an under complete autoencoder. Over complete autoencoder, obviously, it's the exact opposite. It is uh, when the hidden layer size is actually larger than the input size, right? So Here we have an example. Assume that you have a n-dimensional input and k-dimensional hidden layer where k is greater than n. Which of the following is true? So that we have certain properties of an autoencoder setup like this, which is in fact what is called as an overt complete autoencoder, right? Where k is greater than n. And the question is, which of the following is true? Is it that overfitting is likely to occur, regularization is required, or is it that overfitting will not occur, right? So yeah, once again, I will give a couple of minutes and then we'll talk about overfitting autoencoders. Mm, okay, so yeah, maybe, uh, so A and B is actually correct, right? And we'll talk about why this is right. So basically, what I'm saying is that when you have an overcomplete autoencoder, uh, overfitting, I'm saying that overfitting is likely to occur, right? Which of course means that option C is not possible, right? And in fact, a corollary of, so basically if option A is true, then a corollary of option A is that option B is also going to be true, right? Because if there is overfitting that is occurring, then have to have some way to prevent the overfitting, right? You have to have some way to prevent the overfitting and learn meaningful features, as it is being said over here. And typically, regularization is one method that you use to prevent overfitting, right? It's a broad umbrella term for uh, methods and approaches that kind of help you to deal with overfitting problem, right? So, the crux of the argument is that overfitting is likely to occur in a situation where you have an over complete autoencoder, right? So if you prove this part, then the remaining option B kind of follows from it, right? By definition. So how do we show this in a simple manner that this is something that is likely to happen? So you can think of a network, right? So you have an input, right? Let's say you have 3 neurons in your input. You have 4 neurons in your hidden layer, which is more than the number of neurons you have in your input. You have 3 neurons in your output, obviously, because it's an autoencoder, right? So now because there are more neurons in your hidden layer, what can happen is a situation like this, right? So you can have a situation that while training the network, uh, automatically it kind of falls into the situation where you know, they your network basically just passes the values from input to the output, right? So it can have something like this can happen. And if something like this happens, then you basically are not learning anything, right? So you have not learned any meaningful features from the data. You're just transferring. You're just kind of bypassing the information from the input layer to the output layer. This is just like it's just like a highway through which the information is passing, right? So this has not learned anything. And once again, because the training algorithm, the stochastic gradient algorithm is heuristic, right? So it is a greedy approach to try to solve these problems. And when you apply greedy approaches, you get these kind of optimal, suboptimal kind of solutions. I won't even say that this is a suboptimal solution because it kind of perfectly matches what you try to do, but it's a trivial solution nonetheless, right? So when you use kind of heuristic, you often get these kind of trivial solutions, which is a problem, right? So if with that, I hope it is established that if you have a overcomplete autoencoder, it is likely to overfit. And if it overfits, then you do regularization, right? So, speaking of regularization, we're going to talk about some of the regularization methods, right? So, one of the regularization methods is called L2 regularization, with a common form of regularization for the neural networks in general. Uh, this is done by adding this additional term to the list, right? So this is lambda times 2 norm of W, where W is of course your weight matrix, and this norm is nothing but the Frobenius norm, so-called Frobenius, right? Where you basically what you do is that you take square of all of the elements in the matrix and then you add them. That's all you do, right? So you apply this regularization into the network, and then the question is, what impact does it have in your training your model, right? So does it prevent the shrinkage of weights? Does it prevent the growth of weights? Does it encourage sparsity? Does it allow the weights to explore the entire uh, weight parameter space, right? So yeah, so think about this. Basically, you're adding this term to the loss, right? I mean, think about what that implies for the values of the weight, right? So what that implies for uh, the weight values that are present in this, and how the values of the weights relate to the loss that you get. And remember that you're always trying to minimize the loss. So yeah, once again, I will give a couple of minutes for you to kind of reason through this, and then we will discuss the solution. Hmm. So, so here we are dealing with what is called as L2 regularization, right? L2, of course, coming from the fact that we are using the 2 norm, right, which is a square norm, uh, also called the Frobenius norm for matrices. And basically, what we are going to do is that we're squaring all the elements of this weight matrix, and we're adding them all up with this positive uh, value lambda, multiplying with this positive value lambda, and adding that to the weights, right? So essentially what this is doing is that if the weights, if you consider, let's kind of zoom into one particular weight, right? Because if we can understand what is happening as a result of one particular weight, then we know on an aggregate what is happening with respect to all the weights put together, right? Because the operation that you're doing is identical for every weight value that is within this weight matrix W, right? So if we understand what is happening with respect to one particular weight, then we will understand what is happening with respect to the entire matrix, right? So given one particular weight, small w, within this weight matrix W, what we are doing is we are taking the square of it, and we are adding that square even with some positive lambda multiplier, and we are adding it to the loss, right? So whatever the value of W, we're adding a positive value to the loss, which means that the loss is going up, right? Uh, in fact, when the absolute value of this weight increases, the loss also increases, right? Because we're squaring, it doesn't matter if the actual value is positive or negative, we'll always get a positive value, right? And then we add that positive value into the loss, right? And essentially what we want to do is minimize the loss, right? So if we minimize the loss, that is the same as saying that we want to minimize the absolute value of uh, of the weights, right? Which, if you consider these options, it actually matches exactly with option B, which is saying that it prevents the growth of the weights, right? So it prevents the weights from becoming very large. That is what L2 uh, regularization actually does. So, like I said, lambda times norm of W penalizes high value of weights, and because of that, it reduces it, shrinks them towards zero, right? And it prevents, high value makes them smaller, right? Of course, it actually does not make the weight sparse, which is different kind of regularization that actually tries to do that, right? Uh, yeah, so like I said, if we come to sparsity, we can say that sparsity is also a type of regularization. Let's say there is a sparse autoencoder, right? And uh, is the entire autoencoder itself is what you call as sparse, right? And the question is, what characterizes even autoencoder as a sparse autoencoder, right? Is it that the number of neurons is less than or greater than the input layer? Number of neurons in the hidden layer is less than or greater than the input layer. So that neurons are inactive or active most of the time, right? And if you think about what is the definition of sparsity and sparseness, then this should be fairly simple to reason out, which is the correct option to choose. So yeah, so a couple of people have answered. Yeah, like I said, it is fairly straightforward to understand what this is supposed to mean if you understand the meaning of sparsity, right? Sparsity just means that most of your values are zero, right? And if values are zero, then other way of saying is that all of those units are inactive, right? They're not doing anything. So when you talk about a sparse autoencoder, what it means is that most of the neurons are inactive or zero valued most of the time, right? Only few neurons are actually active. They are kind of generating some zero value, and that is what makes the autoencoder so sparse, right? So this one, option C is actually the correct. Obviously, A and B are the definitions of under complete and over complete autoencoders, which neither of them actually kind of have any direct relation with sparsity. And D is the exact opposite of sparsity, right? So D is what is called as a dense. Uh, when everything, when things are uh, active most of the time, right? Uh, that condition is called as a dense activation or a dense weight matrix or things like that. So yes, sparsity just correlates with inactivity or zero values, right? So that's why it's important. So if you consider an autoencoder where inputs are real values, right? So this is like a previously we had discussed problems in thinking about classification problems and regression problems, right? So this is kind of similar analogous to that. So the inputs are real values. The question is which of the following is describes the kind of activation function that you would require at the decoder side, right? At the output side. So you have different options for the possible activation function. The question is which one is most appropriate. In fact, we also have like on the encoder side, uh, we have some options, right? So we have one option that talks about the encoder side, which is the uh, the activation function of the hidden layer that forms the encoder uh, of the uh, encoder decoder autoencoder structure, and the rest of the options deal with the decoder side of things. Mm. Okay, so let's see what are the options, right? So going through the option, we can kind of figure out which ones are correct, which ones are not correct, right? So first of all, notice here that inputs are real values, right? What this means is that outputs are also real values, right? Because we're talking about an autoencoder, inputs and outputs are the same thing, right? So if inputs are real values, then outputs are also real values, right? And what is the best uh, activation function to uh, generate real values is basically no activation function, right? So what you actually want on the decoder side, right, where you want to generate the same kind of value as the input, what you want is basically nothing, right? You don't want any activation function. You basically want a linear activation function, right? So C is one of the correct options. Linear activation function can be used for the decoder because you are kind of aiming for real value outputs, right? The other part is, of course, if linear can be used or linear should be used, then it means that something else cannot be used, right? Which means that A is also true, right? A is saying that tan H cannot be used for the decoder. This is true because what we want to use is linear, we don't want to use tan H, right? So A and C are the correct options. Uh, the other options so one of the other options is talking about the encoder. So here it doesn't really matter what we use in the encoder, right? What activation function we use in the encoder, because this is the hidden layer, right? So the encoder is the hidden layer. We don't really know what is happening, what happens in the hidden layer, right? As long as we use some kind of nonlinear activation function in the hidden layer, we are fine, right? Because we need a nonlinear activation function to separate out the action of these two weight matrices, right? So we just need this activation function to be some sort of nonlinear function, right? As long as it is nonlinear, it doesn't matter. We don't really care if the hidden layer activation function is sigma, tan H, ReLU, or whatever, right? So it can be sigma, right? Which is what I'm trying to explain. So, we cannot say that it cannot be sigma. Similarly, sigmoid activation can be used for the decoder. This is obviously not true because we are looking for real values, and for real values, like we have already discussed, proper the kind of optimal activation function that you might want is linear, right? So D is not true. B is not correct because of that. B is not correct because we can have anything in the encoder activation function, the hidden layer activation function. So we can have sigmoid also, and the remaining have already discussed. Right. So finally, we come to Jacobian matrices. So a Jacobian matrix is nothing but it's a multi-dimensional uh, expansion of of differential relations, right? So consider you have like it's one-dimensional function, which have y equals to some function of x. When you take a partial derivative of y with respect to x, you get del y del x equals to something, right? Uh, the Jacobian is that, but expanded to multi-dimensional maps where x y belongs to r m m dimensions, x belongs to Rn, and f is a function that maps from Rn to Rm, right? So if f is a function that maps from the n-dimensional space to the m-dimensional space, then how do you talk about the partial derivative of the function f? Uh, we now talk about what is called as a Jacobian matrix, right? Which is basically J of uh, J denoted by J, where J of I comma J is nothing but gradient partial derivative of yi with respect to xj, right? So this is, you know, the ith element of y what is the relation of the ith element of y with respect to the jth element of x, right? How xj is connected to yi, basically, right? And if you think about matrix vector products, right? So if f is nothing but multiplying by a matrix, let's say, right? So you have a m by n matrix w, right? And then you multiply, you say w times x, y equals to w times x, right? So you can have something like that. Uh, then you will have some Jacobian, right? And it turns out that when you have y equals to w times x, this is nothing but a linear relationship, right? Because multiplying matrix vector products are linear transformations. So the Jacobian of this f of x, this linear transformation, is nothing but w. In fact, it is like w transpose, right? Because it has to go into the opposite direction. So Jacobian is obviously important because this is actually how you compute the this is how you compute the of uh, gradient that has to flow through your network during the backward pass, right? So compute the gradient. Uh, Typically, you don't need the full Jacobian treatment because the values like uh, the activation functions, for example, they are element-wise mappings, right? Typically, they are element-wise mappings, except some special cases like the softmax activation function. Uh, but, yeah, so typically you don't need this Jacobian treatment, except for the very simple case of matrix vector products, in which case the Jacobian is nothing special. It is just the transposed form of the weight matrix itself. And in fact, if you think about more complex, you can think about like more complex operations. For example, it has not been covered yet, but you can think of convolutional operations, right? So you have a convolution operation, and in fact, what it boils down to, that convolution operation is nothing but a matrix vector product, right? So you can basically conceptualize the convolution operation as a matrix vector product, and then you can do the backward pass by thinking of that matrix vector product representation and just taking the transpose of that uh, matrix to do the backward pass, right? So yeah, so this Jacobian is generally speaking, it is kind of important when you're dealing with functions in higher dimensions, but when in the case of deep neural networks, deep learning, uh, the most the most often encountered case that you will see is nothing but the linear transformation, in which case is nothing special, right? So here finally we'll have one question that kind of deals with Jacobians. So you have this uh, you have this multi-dimensional equation, right? So you have uh, one vector ABC is a function of the vector x, y, z, right? So you have this vector x comma y comma z, and then you apply a function and you get a comma b comma c, and the function is described as such, right? So it is described as a equals to 2x plus y plus z, b equals to x plus z, c equals to 3z. The question is, what is the Jacobian of a comma b comma c with respect to x comma y comma z respectively, right? So if you're thinking in terms of the Jacobian matrix, it's basically the diagonal elements of the Jacobian matrix. That is what I'm asking, right? So it's like I'm asking gradient of A with respect to X, B with respect to Y, and C with respect to Z, right? So yeah, try to figure it out, and then we'll see, we'll discuss the solution. I think this is the last question, right? Yeah, it is it for the last question. Okay, so mm, yeah, so C is in fact the correct answer here, right? Like I said, uh, if you kind of explain, if you explain what this is, right? It's fairly simple to figure it out, right? I said when you explicitly say that what you want is gradient of A with respect to X, B with respect to Y, and C with respect to Z, right? What I'm saying is that I want del A by del X, del B by del Y, and del C by del Z, right? And del A by del X, you just take the gradient of this with respect to X, you get 2. Take the gradient of B with respect to Y, you get 0. C with respect to C, you get 3. So you get 2, 0, 3, right? The other way to look at it, of course, like I said, is the idea of a Jacobian, right? In this case, you have a three-dimensional vector that maps onto another three-dimensional vector, right? And in fact, this mapping that you have here is a linear mapping, right? Because each of these equations is a linear equation. They have three linear equations in three variables. You can say that x, y, z are the uh, free variables, ABC dependent variables. Right? This is a linear function essentially, and in fact you can represent it as a matrix vector product. Right? Like I said, you can do just you can do you can basically write out these equations, right? If you write x, y, z as a vector, then each of these equations, the coefficients of x, y, and z, they are nothing but the rows of the matrix, right? So you get first row is 2, 1, 1, second row is 1, 0, 1, the third row is 0, 0, 3, right? So you get this thing. And then if you take the Jacobian, uh, with respect to ABC in the left and XYZ at the top, get like I said, because this is nothing but a linear transformation. When you take the Jacobian, you get the exact same thing, right? And uh, the diagonal element is in fact exactly what I asked, which is nothing but 203, 203, right? So yeah, fairly straightforward stuff. That's Jacobians. Uh, we're kind of done with this autoencoder questions, right? What I want to do, I would like to do now is to do a little bit of hands-on autoencoder coding, right? So we'll see an example, basically. Mm, yeah, okay, let's see. Share screen. Very good. Uh, okay, let's see. Oh, okay. Okay, so let's dive into, like I said, autoencoder example, right? Hopefully the screen is visible. Yeah. Uh, yeah. So sorry, this way. So MNIST autoencoder. So this is I think but so this is what is called as a IPython notebook, right? And what I'm using here to run it is Colab, which is a Google Cloud service that kind of enables you to run this deep learning kind of experiment stuff on the cloud, right? On Google, Google GPUs. In fact, if you want to use GPUs, you can use, there's some limited kind of free availability that they allow for people to use, right? So yeah, for this kind of a small thing, you don't really need GPUs. So let's start over here. So this starting part, uh, is then we are just setting up the environment, right, to do what we want to do, which is in this case we want to do a uh, autoencoder, right? And we are going to use so we'll use TensorFlow here. Right? TensorFlow is one of the frameworks for deep learning. We're also using Keras, which kind of helps to make the work of making models very simple. And we are using TensorFlow datasets to grab our MNIST dataset and work with it, right? So these are the main things over here. TF dataset. So this is second part here is nothing but, so we're constructing the dataset, right? So we have grabbed this MNIST dataset, split it into train and test, right? And we have generated two datasets, right? So there is one TS train, which has 60,000 items, 60,000 training samples. Then we have TS test, which has 10,000 items, which is 10,000 training samples, right? And then we display some like four of these samples, right? So you basically have things like this, uh, images of handwritten digits, and their labels, right? So you have the image and you have the label alongside it, because MNIST is actually a classification uh, dataset benchmark, right? So you classify images and you say what is the digit that is present inside them. So the next thing that we do is normalize these values, right? And here I'm doing something a little atypical, right? So here there is this function normalize image, which takes basically this whatever you get inside this data frame, TFTS data frame, which is image and the label, right? And this image that is present in this dataset is an 8-bit unsigned integer image, right? So it goes from 0 to 255. What we are going to do here is basically we are going to compress that to the range of 0 to 1, right? Which is why we first cast it as a floating point and then we divide it by 255. So now the output is lying in the range of 0 to 1, and then we reshape it into 28 by 28, right? So by default, what you have, these images, the shape of these images is 28 by 28 by 1, because it has one channel. It has 28 by 28 in 28 rows and 28 columns, and it has one channel, right? Because it is a black and white image. So we kind of don't need the channel, so we get rid of it. And the next part is, so here I'm making a little bit of a change. I'm kind of discarding this label, right? So the input is being reshaped and uh, normalized and reshaped, and then the target is also normalized and reshaped, but the target is reshaped to a flat vector which has 784 values, right? Which is 28 times 28, and then returning this input and target, right? So input and target are in fact nothing, in fact the exact same values, right? Input has 28 by 28 shape, the target has 784 shape. We can also have both of them as 784, right? That is also fine. So we then map the normalize image function on top of on the TS train in the train data set, and we create these batches of 50 images each, do the same mapping to the DS test as well. We don't shuffle the test dataset because we don't need to shuffle it, right? So this, run it, it's done. Now we are defining the model, right? So this is, so here is question, first question. What kind of a, what kind of an autoencoder is this, right? Is this a word complete autoencoder or is this an under complete autoencoder? Yeah. What is this? Is this word complete or under complete autoencoder? So this is first question, uh, right? It's word complete. That is number one. Number two is how many parameters are we dealing with? Terms. There, this. So here is the model definition, right? So the first layer is a nothing but it's a flattened layer. So it takes this 28 by 28 input and it flattens it to a single vector, 784 dimensions. The second layer is a dense layer with a 10H activation, and the third layer is a dense layer with a sigmoid activation. Right, so that's all that we are having. That's all that we have in this model. And yeah, very simple questions. At this stage, you should be answering these questions, you know, just like that. Because we have been doing this for multiple weeks, uh, dealing with how many, counting the parameters. Uh, this session, we have talked about extensively about over and under complete autoencoders and so on and so forth. Okay. Uh, yeah, so this is in fact indeed an undercomplete autoencoder, right? It's correct. Because yeah, just we're going by the definition, right? So input and output layers have 784 neurons. Uh, what we have here is just 40 neurons, right? In fact, let's reduce this even further. Let's do 10 neurons. Let's see what happens, right? So our middle layer, right, our hidden layer uh, right now has only 10 neurons, and then you're trying to get 784 output pixels out of it, right? So we define the model, and once you define the model, it will tell you how many parameters are there, right? Which is, I think, which is fairly straightforward, right? You have uh, 10 by 784, right? And then which is, so 74 to 10 is 7,850 parameters, right? Which is 74 times 10 plus 10, right? Biases, 10 biases. And then from 10 to 784, we go, it's kind of same, but the number of biases are larger, right? So you go from 10 to the number of weights is same as 7840, but the number of biases that we are going to add now is 784. So you add 784 to 7840, you get 8,624, right? And the total number of parameters is very small. It is just 16,000 something parameters, and this is like an extreme compression, right? So you have inputs that are that have 784 values, and you're trying to compress them to just 10 values, right? And let's see how well this does. So we set up optimizer, we set up Adam optimizer, right? So we talked about optimizers in the previous session, right? Or one of the previous sessions, I don't remember exactly. But yeah, so this talked about basically different kinds of optimizers, right? So you have simple gradient descent, you have momentum, you have item optimizer, and then you can play around with the batch sizes and stuff, right, to see what happens. So we set up our optimizer, and so here is where we do things a little bit different again, right? Because this is a okay. Yeah, so because this is a autoencoder, uh, we want mean squared loss over here, right? Because yeah, so because this is a autoencoder, we are trying to match the input to the output, right? So the loss that we're going to use is just mean squared error, and the metrics that we're going to display to uh, kind of track how the training is going is also going to be the same thing, right? So we're going to use mean squared error as the metric. So we have set up our model. Finally, there's nothing left but to train it. So just call model.fit, right? And this trains the model. Trains uh, with dataset training for 10 epochs. Validation is done on dataset test. And you can see the values of uh, the mean squared error doesn't seem to be going down, right? So it's kind of stuck at this 0.067 value. And we'll see, we'll do a couple of repetitions of this, and we'll kind of figure out what is happening, right? So, yeah, so we have this. So there's a drop at the beginning, and then nothing, right? It's no longer kind of fitting anything more. In fact, train has kind of fallen below the test, validation, which means that there's typically there is going to be no further improvement of this model, right? And then we can uh, plot an example case, right? So this is our kind of input, and if the autoencoder was trained properly, we would have seen something like a 2 over here, right? But we are not seeing something like that. We are seeing something very, very odd, kind of looks like an 8 or a 9, or some sort of weird thing. So obviously, this network is not doing very well, right? And so one of the things that could be the issue is that, so obviously, this is a very simple autoencoder. We have not added any complications, any bells and whistles to it. So well, the straightforward thing that we can do, of course, is kind of control or reduce the amount of undercompleteness that we're doing over here. So we increase this to 20, let's say, and try to see what happens, right? So we have now about twice the size of the model. We do the same thing, train the model, and then try to see what we get. And nothing seems to have changed much, right? We are still kind of stuck at this 0.067 uh, error value, right? Which means, I don't even need to really see the output. I can estimate based on what I'm seeing here that it's not going to be very good. Okay, right? So yeah, the same as before, right? Stagnates after one epoch, then you get something very similar to the previous output, right? So this is clearly not working. So let's try to increase it a little bit. Let's do 30. See what you get. Train the model, generate this. So now we seem to have some kind of a breakthrough, right? Because now we can see that this loss is going down, right? It's not stuck at that 0.0767 value anymore. It is going down to 0.2045 or something. So hopefully we can see slightly better output, right? But even then, it's kind of saturated at this 0.04 value. Okay, so it is kind of saturated at 0.043, and if you see the train and test, validation is tracking very well with the train, but they are kind of reaching the same converging, and we continue training. Most likely the training will go below the validation, right? And here we have something little different, but it is still not good, right? So it's like it has captured this kind of uh, this thing, right? So it has captured this shape of this tool, right? That's going from here to here, but it has not accurately like captured the tail that you get. So if we just increase it a little further to 40, you can see. Right. So this is progressing even faster, right? So we are no longer stuck at that point. 043 values, we're going in fact below, we're going 300, 200, that lower values, right? So now we have, yes, yes. Uh, so you use the same techniques, right? Uh, the general techniques for machine learning and specific techniques for deep learning, the same. So how you handle unbalanced data set in general machine learning is the same as how you handle it in deep learning, because the data part of it is common to both, right? So it's nothing different. So now we have something much better, right? So we have this is this does kind of approximate what you are getting over here, and we can see some other examples as well that we can see. Uh, See some other. So we have 50 examples. Let's click up 16th, 14th, 16th example. Yeah, so this is a 4. So this has captured kind of uh, the appearance of that 4, right? See another random simple. Yeah, so it is capturing very well, right? Can see that. Let's say 2, 8, right? So you can basically print all of them and see how it looks. But overall, with 40, it seems to be that we are capturing the data very well. In fact, the loss seems to be going down steeply, which means that we can even train it for a few more epochs. Let's say we can train for 15 epochs, and hopefully it will improve even further. Train for 15 epochs, then you can see it. So the basic thing is that, previous examples when we were doing with 10, 20, 30 uh, hidden hidden neurons in between, that was too small, right? So there were simply not sufficient model capacity to capture the features that you wanted to represent. With 40 neurons in the hidden layer, we now have sufficient model capacity to capture the features that you wanted to capture. And because of that, it is now able to represent, it is now able to do this autoencoding more effectively, right? What this also means is that the 784 input values is mostly redundant, right? Which you can kind of see because most of it is actually zero values. So the 784 is like mostly kind of redundant information that is not required. What is actually kind of relevant information can be compressed to as small as 20, 40 neurons, right? So this is the important thing, which means that you can basically apply this compression, and this is a pretty strong compression, right? So you're going from almost 800 to 40, which is like a 20 times compression, and you are hardly seeing any difference, right? 15 epochs of training, it looks even better, right? So this is a this is the original input, this is the autoencoder uh, output, which very closely resembles what was the input, right? So this kind of tells you it is like how redundant is the information in the actual data, you know, how you can compress that and still get outputs that are very close to whatever you're trying to generate, right? So this is autoencoders. There are many variations of autoencoders. There's variational autoencoders, for example. Uh, there is yeah, so there is a variational autoencoders, and then, like I said, after that you kind of get into this uh, whole. So autoencoders basically is the start of generative networks. So you go from simple autoencoders to variational autoencoders, then you go to GANs, which is generative adversarial networks. You go to conditional GANs and UNets and the diffusion network, all sorts of things, right? So this is the starting point of all of those approaches, of all of those applications. So, yeah, uh, I think this is a good place to stop, right? Covered basically what I wanted to cover. We'll see this backdrop thing at a later session. Okay, so if anyone has questions, now is a good time to ask. Yeah, I will add it to the presentation. I'll share the notebook and I'll add it to the presentation, right? So, yeah, you can access it, you can play around with it, right? And when variational autoencoders are taught in the class, you can try to modify this code into a variational autoencoder as well. That would be a nice like exercise to do. You can also kind of clarify those uh, those concepts of variational autoencoders, right? So yeah, I will share this and other notebooks links to them. Okay, so since there seem to be no further questions, I'm going to end the call. Right?